Welcome to Introduction to Quantum Field Theory, Lecture 13. In this lecture, I will talk about a particular technique to calculate higher order expectation values of the field. The technique that I'll talk about is Wick's theorem, and it will be useful for us to learn about this theorem in order to calculate perturbative results for the pressure of an interacting quantum field theory. Recall that in lecture 12, we said that in order to find the pressure of an interacting quantum field theory in perturbation theory, we needed to calculate expectation values of powers of the field, such as the expectation value of phi 4, the expectation value of phi 4 of x, phi 4 of y, and so on. Now, these expectation values were defined as path integrals of whatever operator we're considering times the exponent of minus the free action, meaning an action that's just quadratic in the field. In this lecture, we'll learn about Wick's theorem and how to calculate these particular expectation values. To jump right in, Wick's theorem states that we can calculate expectation values for a system that has a Gaussian action by decomposing an expectation value of n operators as a sum over all combinations of two of those operators. So instead of having, for instance, 4 operators in the expectation value, we can always break them down such that it only involves the expectation value of 2 operators. We'll call these things 2-point functions in the following. For the example that we discussed in the previous lecture, the first order perturbative result for the interacting quantum field theory lecture with a phi 4 interaction, we were asked to calculate the expectation value of phi 4. Phi 4 basically has only quadratic terms, meaning all the 2-point functions that we can build out of this involve phi of x, or phi square of x. That means that the properties are always phi squared of x squared. And there are exactly 3 possibilities to come up with these 2-point functions out of 4. So that makes up a combination of 3. All of these are equal. So that explains this vector 3 in this result here. What we want to do in the following is prove Wick's theorem, and we'll start with a simple Gaussian integral to elucidate on how this is done. So let me discuss a Gaussian integral over a vector field Vi that has an arbitrary number of components. If I was just a single component, then basically this would just be an ordinary Gaussian integral, but I want to discuss an arbitrary number of these vector fields, and eventually I want to send the number of these vector fields to infinity such that we get a continuous function. So the integral we are considering is the integral over a Gaussian action, meaning an exponent that is at most quadratic in the field V. We'll define this to be equal to some exponent of an unknown function w that has to depend on b because we're integrating over v. I want to restrict our attention to Gaussian integrals where this A here, this matrix A here, is positive, definite, and symmetric. Positive, definite because I want this integral to be well-defined and convergent. Bi here can be an arbitrary vector, and we can solve this integral because it's Gaussian via variable substitution. So if we let Vi go to Vi plus the inverse of the matrix A times Bj, we plug this into this integral here, we find that there's one term that is independent of V, that's just the exponent of -1/2 B inverse of the matrix AB. And then we have an integral that's just purely Gaussian and not dependent on B. We find that this integral that's not dependent on B is just the same as setting B is 0 in our original definition. And we find that basically the exponent of W is just the exponent of W at 0 minus 1/2 B inverse of AB. In the following, I will call e to the power of W of beta or B the generating function. called the generating function because I can use this function to take derivatives with respect to the vector b, and I can use this function to generate expectation values of the field vi. This is true because if I take the derivative with respect to bi of my generating function, I can pull through the derivative I can pull the derivative through the integral because the integral is over b and I'm deriving with respect to b. These are independent. And then I'm asked to take the derivative of an exponent with respect to the vector b. This is easy to do. It will just bring down 1 power of this vector field v. So we get an integral over vi times the original Gaussian form. If we set b to 0 on both sides, then basically it means that the b in the exponent just drops out, and basically we are left with an integral that's just effectively the expectation value of vi with respect to a quadratic action. So we call this expectation value of vi times e to the w0 because that's essentially what this represents. We can repeat this process an arbitrary number of times. So we can do derivatives with respect to bi, bk, bl, and so on and so forth, bn of our generating function, and at the end set b to 0. And each of these derivatives will bring down 1 power of the field, so that we end up with, on the right-hand side, the expectation value of n of these fields times e to the w of 0. We calculated the generating function in our Gaussian integration earlier, so we can take the result from 13.6, plug it into the formula from above, and we find that this expectation value here is equal to taking n derivatives of our generating function here. Note that the e to the w of 0 has cancelled on both sides. We can then expand the exponent here in powers of b. So we get that the expectation value of n of these fields is equal to taking the derivative with respect to n of these vectors b of something that is 1 minus something that's quadratic in b, something that's quartic in b, something that has 6 powers of b, and so on and so forth. There's always an even powers of b because the result here just comes with 2 powers of b in the exponent. Having expanded this exponential of the quadratic form in b, we find that there are a number of consequences for the expectation value. For instance, the expectation value of 1, so no operators, is equal to just unity. Whenever we have an odd number of insertions, such as vi or vi, vk, vl, or 5 of these, we always get 0. That means that, the reason for that is basically that our form is quadratic. So if we take an odd number of derivatives of a quadratic form, we always have to derive with respect to something that doesn't depend on b, so we always get 0. The expectation value of the 2-point function is just the inverse of this matrix I. And if we have 4 of these fields in here, then basically we get all possible combinations. So we get aij to the -1, amn to the -1, aim to the -1, ajn to the -1, ain to the -1, ajm to the -1. However, note that these individual inverses of these matrices are nothing else but the result from calculating the 2-point functions. So we find that if we have a 4-point function, that naturally sort of separates into the sum of all possible combinations of 2-point functions that we can build. Higher order expectation values, meaning even multiples of v, then just generalize this result such that you get that an arbitrary number of correlation functions that is an even multiple of v is just given as the sum of all possible combinations of the 2-point functions that are contained in this expectation value. Finally, if we let the number of vectors vi tend to infinity, we get a continuous field, v of x. The results that we discussed in the previous slides remained completely unchanged because they don't depend on the number of vector fields. And just renaming v of x to phi of x, this just proves Wick's theorem 13.3. That concludes the present lecture.